Welcome to Walkabout the Galaxy, Are you sure this is an astronomy podcast? Astronomy podcast, where the science is universal, the opinions are personal, and the hosts cannot be simply reduced to a mere adjective for the sake of your standard intro, Josh. We are Strange, Charm, and Top, the Astroquarks, also known as Josh Cole, Addie Dove, and Jim Cooney, coming to you from the Walkabout Studios at the University of Central Florida. Be sure to stick around at the end of the episode for a collective sigh of relief. Christmas is coming up. Be sure to check out on our website our sweet WTG shirts.
Yeah. What a great Christmas gift.
Or any kind of gift.
Or a Hanukkah gift. You could get 8 of them.
Or a
self-indulgent Festivus.
Festivus gift.
A Festivus for the rest of us.
That's right.
Or just a therapy shopping purchase.
Did we have a Cyber Monday sale?
We did not.
No, never mind.
Yeah.
It's past that anyway, so it doesn't matter.
Right. That's true.
We totally did.
We did. Sorry, everybody. If you're listening to this on Cyber Monday 2019, shirts are half off. Our stumpers are Skywalkerial.
Oh.
Jim.
Yeah.
There's been how many? There've been 8 and almost 9 Skywalker saga movies, I guess, right? And then 2 side spin-off movies.
Right.
But the main Star Wars saga, I guess, is really just about the Skywalkers.
Right.
Because everything else isn't really, or something, like The Mandalorian and all that other stuff.
Oh, The Mandalorian's good.
I've been enjoying it, yeah. All right, so anyway, there have been 8 movies out so far. We know the title, the 9th, and they're all either one title or the other. So, yours is The Last Jedi or The Return of the Jedi.
Oh.
Well, Return of the Jedi. I mean, I'm old, and so I still cling. I mean, I've enjoyed these last few movies for sure. And I'm not totally on board with all the haters, but
you sound like that's a bad thing. Like you're disappointing people. It's like I'm not totally on board with all the haters and the trolls.
I'm sorry.
It's like I wish I could be.
I want to be cool like that. No, I've enjoyed them and I thought they were good, but I liked Return of the Jedi. I'm also not on board with haters because I often hear, when people are talking about the original trilogy, how like The Empire Strikes Back is so good and The Return of the Jedi kind of sucked. I thought it was friggin' awesome. I loved the Ewoks and all of that stuff.
Yay! I also like the Ewoks.
I enjoyed that movie.
Yeah. I actually just watched, I think for the second time, the honest trailer of The Last Jedi. You know the honest trailers?
Yeah.
So they did an honest trailer, which was a funny sort of mix of this is an awesome movie and this is a terrible movie, so it's sort of like a debate back and forth. Nice. These are on YouTube if you don't know what about honest trailers.
That's a debate I'd watch.
It was really good, actually, and the thing about it was I agreed with most of the good side and most of the bad side.
Yeah.
Like, I liked a lot of the thematic things that they did in The Last Jedi that I guess some people are pissed off about.
Yeah.
But I also was really, really irritated by some of the storytelling things that they did. And I wasn't irritated by, I guess some haters are hating on it for some, like, I don't even understand some, like, I guess they don't like the thematic, like, there's no special bloodline issues or whatever.
Oh.
Some people are upset about that. Anyway, Addie.
You know what was even better, by the way?
What?
Ewoks, The Battle for Endor.
Did you just look that up?
I looked up at the title because I remember watching those. There were 2 Ewok movies, made-for-TV movies that came out in the 1980s.
Yeah.
There was also
the Christmas
there was
Chewbacca movie.
Yeah.
What?
Caravan of Courage and Ewok Adventure.
You've never seen the Christmas special?
No.
The Chewbacca Christmas special? You learn the history of his family and stuff like that.
Is it animated?
No, it's a live-action, really terrible TV quality thing. You've never seen that?
No.
We have to watch that.
How did Lucas let that happen? How did he let terrible, cheesy TV stuff get made?
It's not clear, but we just watched a funny, weird mashup thing. I guess, I don't know, it was Harrison Ford and Call of the Wild. Anyway, there was it was called The Call of the Wild, but it was like Harrison Ford and Chewbacca. And
so Harrison Ford has got, The Call of the Wild is coming out soon.
Oh, that must be.
Is
it a new one?
It's new, yeah. Starring Harrison Ford.
Didn't they do one not that long ago?
No.
Oh.
This one's coming out. Casey worked on it. My brother is the first AD on it.
So so this explains why this is so it was a mashup trailer where they had like his voiceover or whatever from the actual movie, but then they clipped scenes from Star Wars, and they also included a bunch of the Chewbacca Christmas special scenes.
I remember shortly
after
Episode 4, original Star Wars came out, and I was like total Star Wars fanboy. Carrie Fisher was on Saturday Night Live. That was in the early days of Saturday Night Live, and she was doing silly stuff, and I was like, Princess Leia can't be doing that. She can't be doing silly stuff. This is outrageous. Addie, Revenge of the Sith or The Empire Strikes Back?
I'm going to also go Empire Strikes Back.
Oh.
But that one's an even easier one than Jim's, I think. Revenge of the Sith was not a great situation. It was... I forget which one. I actually have only watched all of those like a couple times probably, and it's been a long time since I watched that set of 3, trilogy, if you will.
Yeah.
So that's all I have to say about that.
Okay. Of the original 3, episodes 1, 2, and 3, what's your favorite, though?
So episodes 4, 5, and 6?
No, 1, 2, and 3.
That's what I was saying. I don't remember.
Okay. Because Revenge of the Sith was my favorite of those 3, I think.
Yeah.
Although it was very much like, oh my God, there's 20 minutes left. We've totally got to wrap up and set everything up that happens in the next trilogy.
Yeah.
Quick! Just got to have twins and name them.
We got to set things up.
Yeah,
I really like, we've been watching The Mandalorian. I really like that. It's interesting.
It is. So The Mandalorian.
It's so freaking cute.
The baby Yoda has broken the internet.
I know. It's so cute.
So it's of course not Yoda.
Well, no.
Right.
We don't know.
But we don't know
who it is.
Right?
Maybe it's a reincarnated Yoda. You don't know.
Yoda isn't dead yet when
that
happened,
is
he? Oh yeah, that's right. Yeah.
Maybe I did go off on this the other day when I was at
on how cute it
one
was?
of the other Quark's house there on the Yodas.
Oh yeah.
But how I've not seen them.
Oh yeah, you're mad.
I'm mad, but my gears are grinding.
About what?
About the stupid baby Yoda.
What's the problem?
My problem was
it looks like Yoda.
It's because it looks like Yoda. I always thought like Yoda. You see Yoda in that thing, and he's like this.
You don't think he's
tiny
a species?
gnarled thing. And I thought he looks like that because he's a zillion years old.
You thought,
and I know he's not like he's not a human. I know he's an alien.
You thought he looked like you when he was young,
right?
Because you're fantasizing you'll eventually one day look like Yoda.
I was thinking about some kind of transformation, like not thematically the same, but the transformation of like Smeagol to Gollum, right? That kind of thing, like. Not for the same reasons, but like because of age. Like he's like I was expecting.
Like getting older and shriveled with age, just like other things do.
Yeah. But this thing looks just like like Yoda, except tiny, and I don't like that.
Younger.
It doesn't look that much younger. He still looks a little bit, but he looks still
wrinkly.
similar.
It's like a fresher green.
I don't like it. That's true. He was. He's a more chartreuse.
Yeah. So this is so for people who haven't seen what the heck we're talking about here. The Mandalorian is an original live-action Star Wars show on Disney's new streaming service, of which there are now, how many streaming services are there? Too many to count.
53 million.
And so it's set in between episodes 6 and 7, I believe. It's after The Last Jedi.
Yes.
It's before
the new trilogy.
that other one, the Force Awakens or whatever.
Yeah.
And so... And it's somewhere, and it's about some bounty hunter who looks like Boba Fett. They all have to wear helmets all the time.
He's a Mandalorian.
How does he eat?
He can take off his helmet,
he
just
says
not in front of people.
He says
he says he hasn't taken it off in front of people. She clarifies with him.
The one I heard, somebody goes, have you ever taken your helmet off? And he goes, no.
Yeah, in front of people. He does clarify that.
All right. Okay. Anyway.
Because that's why she brings him food to eat, and then she leaves.
There's a child... There's a child creature that is green with pointy ears and 3 fingers or something.
Yeah.
A Yoda-looking.
He looks like Yoda, but a little baby, slightly fresher green, big baby eyes. Yoda.
Yeah. And makes cooing baby sounds.
Oh man, the first episodes we watched, Akbar was over, and we were watching with subtitles on, and it just said like cooing noise a bunch of times. It was really annoying.
All right.
So this actually is a podcast, not about astronomy.
Right.
Apparently not.
Predictive text.
Are you sure this is an astronomy podcast? Well, today we are talking about a giant black hole, a disintegrating asteroid, a supernova. So those are all astronomy things. But first, this episode of Walkabout the Galaxy is brought to you by classical mechanics. Are your forces not giving you an equal and opposite reaction?
Oh, no.
Are your springs not giving you simple harmonic oscillation? Is no angle small enough to make your pendulums behave? Well, bring your troubles to the expert technicians at Classical Mechanics. We're trained to deal with anything on the macroscopic scale. Our trained staff have certificates in each of Newton's laws of motion, as well as Lagrangians and Hamiltonians. So if your walk about the galaxy is getting tripped up, come see Classical Mechanics for a free, no-obligation appraisal. Our work comes with a guarantee to conserve momentum, angular momentum, and energy. So don't wait for entropy to get you really down. See us at Classical Mechanics now. Classical Mechanics, you're in good hands.
Allstate.
Allstate,
yeah.
Wow.
Easy.
And that was I enjoyed that one. Very nerdy. That's going to really appeal to our nerdier.
The small segment of
our
listening audience that is nerdy.
I also now have a Halloween costume idea.
Oh, is it a classical mechanic?
To be a classical mechanic.
Jim can be a quantum mechanic.
Yes.
Nice.
Oh man. Let me
Who
put it
could
in my
phone. No, you should be a general.
You should be general relativity.
You should be warped space-time. Just put
on
a.
Is that a belly joke?
What?
No.
My waistline has become warped.
No. It's like somehow if you can stretch some black rubber with some circles.
Yeah.
Get a big sheet of black rubber, draw some circles on it, then stretch it around yourself, and you can be warped space-time. And Addie, how would you? Well, I'll be curious to your classical mechanic costume.
Yeah, you're going to find out in a year.
Okay, and I'll try to figure out how to be whatever the hell I am. I don't know. I think we've pretty much nailed nerd news, except you mentioned The Expanse, which ties into one of our science topics.
Yeah, The Expanse premieres on, I think, the 4th or something like that.
You mean
on
the fourth
Amazon
season of it, or the third season or something?
The fourth season premieres on
the
December
4th.
4th, I think, somewhere around there. There's a bunch of other movies coming out soon, maybe before. I don't know when we're going to record next.
The Rise of Skywalker comes up, and we are entering the holiday vacation.
That's true. So you're going to look for fewer episodes over the next month, I imagine.
Our cadence will slow, much as time in a strong gravitational field
slows down.
Right.
Great.
Excellent way to connect.
Yes.
And
there's
to
a bunch
slow
of
down,
launches.
totally
slow down our momentum on our
sucked all the energy out of that light and out of this podcast.
Oh, let's reinvigorate it with some launches.
Okay.
Well, not yet, though. But there's a bunch of launches coming up because everybody's trying to test before the end of the year. I think we touched on this last time.
Right.
But
Why does that matter? Why do they care?
Because a lot of times they have contracts that say they're going to do something by this date. And so,
okay.
now it's almost the end of 2019, it turns out.
Right.
Somehow.
It's
I don't know
racing upon us.
Space time.
Yeah.
There's a Starliner on top of an Atlas V right now. That's Boeing. It's on top of the Atlas V going out to the pad. They're going to do testing in a week or so, but they're doing a lot of rehearsals in the next weeks.
But will they be launching it in principle?
They're launching it for the
abort
test, I think. That's what this one is, right?
So they'll launch it and then it'll do an escape off the rocket?
Yeah,
those are cool.
I know, those are super cool.
Yeah.
Especially if they go well, and kind of if they don't.
This is when the rocket takes off and it's got a capsule that would at some point be carrying people, and then mid-ascent they fire the emergency escape rockets, which plucks the capsule safely away from what would be an emergency with a booster below. And this is something famously, of course, that the shuttle could not do.
Did not have, right.
I forgot.
But all these sort of gumdrop things like the Apollo caps, all of our previous capsules have had this ability to do this.
And there's some of the primary tests a lot of them are doing.
And a Soyuz capsule recently did this.
Yeah, for the first time in since the 75 or something like that.
At quite a high altitude.
Yeah.
Like way
but
up
the astronauts that were on that, and cosmonauts, have since gone to station.
Yeah.
On a successful Soyuz launch.
It just shows that those emergency escape systems are important to have.
Yes.
And when they function right, they can save lives. Which is a good thing.
And there's going to be another Falcon 9 launch or something like that soon, too.
Right.
A bunch of stuff coming up. There's been a bunch of... I know one other fun space news. They found the Indian Vikram, the Indian lander. LRO has been taking images of the surface of where they think it maybe was, and they found... the Vikram Indian lunar lander.
Lunar, on the moon.
Yeah, on the moon. It was supposed to land, but it did a rapid, uncontrolled descent onto the surface. And so they think, they put out a press release, they think the engines worked until certain, and then there was supposed to be this other set of engines that kicked in, and they didn't work like they were supposed to, so it crashed on the surface, and LRO spotted the crash site. So there's a cool before and after, and lots of little, other impact sites.
Secondary
that
debris.
Are maybe secondary debris or something like that. So
cool.
It's cool but sad, but cool. Littering the surface.
Our transitional science topic from the nerd news of The Expanse is that an asteroid, a paper was published recently that describes the disintegration of an asteroid. And this asteroid apparently broke apart because it was smacked into by another smaller asteroid.
And we have images of this.
We have images not of the actual smacking,
right, but of the
thing fading away into invisibility. Yeah, one of the analogies about like when did it break apart? One of the authors said it's sort of like if you put a drop of milk in your coffee. When does that droplet break apart or disappear? It's this sort of gradual,
continuous process, right?
The material is moving away and you see it getting fainter and fainter and fainter, and then you can't see it anymore. So that whole process took a couple of months. So the asteroid that broke apart was P2016 G1.
Well, that means we didn't know about it for that long.
That's true. We didn't get much of a chance to become attached to it.
Yeah.
It's was discovered in 2016, as the name implies. The G1 refers to which half of which month. A, B, C, D, E, F, G is the first half of April, and it was the first thing discovered in the first half of April that was given an orbit by the Pan-STARRS, which is one of these big automated survey things that's been discovering all sorts of cool stuff that we've been talking about. Was the interstellar comet discovered by?
The first one was.
The first one was,
Oumuamua.
but not the second one.
The second
Borisov was discovered by Borisov.
Maybe.
I think so.
Okay.
Yeah.
Yes.
And in any event, we have a bunch of these big survey things out there which are discovering loads of stuff out there. Lots of asteroids, not as many as in The Empire Strikes Back,
No.
or pretty much every depiction of an asteroid belt in science fiction, which typically shows it as a crazy minefield that you have to dodge things, which is why it's somewhat remarkable that we actually saw evidence of two things running into each other.
Right.
It happened a lot early on.
They do it pretty well in The Expanse that we were just mentioning. Like
that's true.
They show they go visit various asteroids in the show, and there aren't a zillion other asteroids in the field of view and stuff like that. It's just a lone asteroid in the middle of empty space, which is what the actual asteroid belt is like. To be fair to some of those science fiction things, like if you have a moon or something that just broke up, then sure, there's going to be a whole bunch of chunks in the immediate neighborhood. But obviously, the asteroid belt or something like that, it really is like one thing, and then a huge volume of space, and then another thing.
Right.
And they don't interact that often. But I guess in this case, they did.
Right. And even though, in fact, many of the asteroids that we see are the debris of something that broke up, but such a long time ago that we have to track their orbits back millions of years to say that, oh yeah, a long time ago they were one piece.
Yeah, a lot of people look at dynamical families and say these are sort of on similar orbits now. We can trace them back in time. They probably started as one thing.
Right. But even if they're on a similar orbit, they're not necessarily in the same place.
Yeah.
Right. Things can be on nearly identical orbits. They'll be very, very widely separated in physical space.
Or even if they're sort of near each other in physical space, if they're moving at similar speeds on the same orbit, they're going to stay. They're going to stay in their lanes. They're going to be fine.
Yeah. So this particular asteroid had a diameter of, the one that was broken apart, a diameter of
400 meters.
All right. I was gonna drop some nasty English units on our listeners, but we won't.
Thank gosh you spared them.
We will not inflict that upon them. And it was, they believe, broken apart by the impact of something that only had a mass of 1 kilogram.
So is this based on like energetic arguments or something?
Yes, so I believe so, because we didn't obviously see that impact.
No,
right?
Yeah.
So there's a lot of interest in this observation because understanding the asteroid belt depends a lot, as well as a bunch of other things. Like in my area, I don't know if you guys know this, but I study planetary rings.
You do?
And rings are a bunch of particles that may have come about from the disruption of some larger thing. So there's a lot of interest in how hard or easy it is to break stuff up. And
also for planetary protection reasons, right? We have a lot of interest in how do you break up an asteroid. And it turns out we now have a laboratory study in space of that happening.
Right. Cool. And this asteroid would have been a nasty thing to come in and hit the Earth. And so if you smack into it with something, kilogram or so, maybe even even 10 kilograms, give yourself a factor of 10 at several kilometers per second, which if you're sending it on a rocket, it's totally a doable thing to have that collision speed.
Right.
You can break it up, and unlike in Deep Impact, whose science, I might add, was otherwise nearly flawless, you do need to break it up. It's not like it's coming into the atmosphere, I broke it up, oh, it's fine. You have to break it up so that the stuff spreads out so it doesn't actually all hit.
Right.
Yeah.
Or all hit in a close period of time and space.
But
that's
all
doable.
That energy.
It's still all coming in. It doesn't from one piece or not. So, but if you break it up in advance early enough, like this thing was, then it all disperses. Like we can't even see that stuff anymore.
Yeah. Maybe some little bit of it is on its way to hit us right now, though.
Maybe, but it'd be a tiny little bit and probably burn up. So how things break up is very interesting, and it turns out that like if you take a rock and hit it with a hammer, what determines how hard it is to break that thing up is the intrinsic material strength of that rock.
Right.
That makes sense, right?
Yep.
But as you get to a certain size, it doesn't actually matter what it's made of. It could be made of feathers or cotton candy. And it's how hard it is to break it up is not determined by what it's made of or how sticky together it is. It's determined by the gravity that's holding it together. So there's a transition from what's called the strength regime, where how hard it is to break something up is determined by the material strength of the thing.
Which is like a rock is as strong as it is, a solid rock is as strong as it is because of the material strength of that rock.
Right, versus like a drop of water would be easier to break up than a rock that size. But if you get to a certain size, then it doesn't matter what it's made of, it's the crushing weight of all the material that is more important than the material strength, even if it's rock.
Right.
And that size actually isn't that big. It's like a little bit bigger than this thing, like a kilometer or 10 kilometers or so.
It surprises me.
Is where that transition is. You would guess it'd be much bigger.
I would have guessed it'd be bigger because there's a similar kind of a dynamic when you're talking about like whether an object is spherical or not, right? So I mean objects are spherical when the strength of gravity overcomes the strength of the rock, and that happens at a few hundred kilometers. Right. And so I would have guessed the same thing for this, but I guess I would have been wrong. Yeah,
it's actually at a lower, and it's partly because what we're talking about is two different rates of strain on it. So in what you're describing, it's slow deformation.
Right.
Put a whole bunch of things together, and how long does it take? How big does it need to be for the weight to slowly warp it?
Right.
And the breaking apart is I'm shooting it with a bullet.
Right.
So I'm delivering a pulse of energy all at once, and what's the response of that? And it turns out things behave very differently depending on whether you're punching a lot of energy into it quickly, or you're just like, here's a big pile of stuff, and let's see what it does. I'm holding my hands out to show a big pile of stuff.
It's funny you mentioned like a cotton candy asteroid, because there was this article.
We found an asteroid that's made of cotton candy. This is big news.
Jim is about to become a planetary scientist now. Screw cosmology.
Oh man, can we start doing some experiments with cotton candy as our material? It's light and fluffy. We think there's like fairy castle structures on the moon. I think we can make this happen.
Okay.
But there's an article from actually like the research article is published back in October, I think. But it just got published this month. But it's there's some researchers who did a study on some primitive meteorites, and they studied some sugars, or they found some sugars, some like early extraterrestrial material sugars, and some ribose, which is present for RNA on these meteorites. So it's possible that there are sugars on asteroids.
Oh, delicious asteroids.
A whole new reason to go asteroid mining.
Oh, asteroid licking.
I know, right? Asteroid
licking.
How many licks does it take?
Let's call the folks on The Expanse and let them know about
this. You need to lick your asteroid to see if it has sugar. Also, it probably has a lot of really bad things. A lot of asteroids have like carcinogens.
Oh.
Yeah, but a lot of the crap we eat also has carcinogens. I eat it anyway, so I'm going to be licking some asteroids.
Those polycyclic aromatic hydrocarbons that we talk about a lot all the time.
Jim's a real asteroid licker.
Those are carcinogens. You are.
I am an asteroid licker. I don't know if that's good or bad.
I don't either.
The title of this episode. Speaking of Jim, we have a special treat today. It's another special edition of Top Cork Trivia.
Top Cork Trivia. That has a nice ring to it.
And we're once again going to go simple. This is not a multi-part thing. This is a one-off. I'm sorry. It's
high five.
Mostly because it was last minute. All right.
As are most things.
And our quiz today, it does require a little bit of a preamble. That's what we often do as well.
When in the course of Astro Cork events.
Our trivia is today cosmological.
Of course.
Which will be a lovely segue into our next topic.
Kind of. It involves Olber's paradox.
I have heard of that.
Yeah.
Yes.
I do not remember what it is.
It's the light one.
Yeah, it's the fact that back in the old days, a few hundred years ago, we were really biased to believe that the universe was infinitely big and infinitely old.
Oh, yes. Oh, I know this one.
Right?
I remember it now.
I know this one.
I just remember it.
And in a universe that is infinitely big and infinitely old, if you were to look out, what should you see?
All light.
Right, you should
light
see
in
uniformly bright. And that's weird. When we look outside at night, we see mostly dark with an occasional star.
A little bit of light.
Yeah, a little bit of light. But imagine the universe is infinitely big. Then no matter what direction you look, at some distance away from you, there's going to be a star there.
Yes.
And therefore, every direction you look, there should be a photon coming at you from that direction. And therefore, every direction should look like the surface of the sun. And that the fact that it's not like that was pointed out by astronomer Olber. I can't remember his first name. Actually, by a number of different people. He just gets his name on it because he was the loudest among those.
I love how these...
Heinrich Wilhelm Olber.
I like how these paradoxes are named after somebody who's like, yeah, but where are the aliens? Or, yeah, but the sky is dark at night.
Yeah, but
it's like, can I get a paradox if I just go, yeah, but, I don't know, the sun is hot or something.
All right.
Yes.
Colwell's paradox.
Figure out, that's got to be a paradox or something.
So, anyway, the question is this.
Okay.
The first person to hint at the correct resolution to this paradox wrote in 1848 the following thing.
There's a lot of context clues.
Yep, that is the
person who can write.
Were the succession of stars endless, then the background of the sky would present us in uniform density, since there could be absolutely no point in all that background at which would not exist a star. The only mode, therefore, in which, under such a state of affairs, we could comprehend the voids which our telescopes find in innumerable directions, would be by supposing that the distance of the invisible background so immense that no ray from it has yet been able to reach us at all. This was written by whom? Or possibly who?
Is this multiple choice or do we have to guess?
Whom? It's multiple choice.
Okay.
A. Ernst Mach. B. Michael Faraday. B. Christian Huygens. Excuse me, C. I'm very good at my alphabet. So that was A. Ernst Mach. B. Michael Faraday. C. Christian Huygens. D. Henrietta Swan Leavitt. Or E. Edgar Allan Poe.
It was very poetic.
He's already playing mind games.
So,
all right, cool.
Mull that over, dear listeners.
We'll come back to that. And speaking of darkness, there was a note about
my soul.
There's there was some black hole. There's some black hole news.
There's
always black hole news.
There's often black hole news. Black holes capture the imagination of everyone.
I guess they particularly capture the imaginations of us. We talk about them a lot.
Yeah.
And we talk about them because other people are talking about them.
Yeah, they're in the news. Every time there's a black hole thing, it gets in the news. When we teach Astronomy 101, as all of us occasionally do, what is the topic that every student wants to make sure you've covered?
Black holes.
Planetary rings. Oh.
Unfortunately for Josh, not planetary rings, but black holes. So anyway, there was a slew of articles recently in the general news about a new black hole that was discovered, and we saw all kinds of titles that were like impossible black hole found and things like this, right? So it was a black hole of 70 solar masses.
Oh.
Unfortunately...
It's worth reminding, I think. Yeah. I forget things.
Oh,
so it's worth reminding from my standpoint. It's worth reminding that when we say, we observe these things, because I think it can be confusing what we say. Not we.
Most of what we say is probably confusing.
We're crystal clear. It should be abundantly clear from this podcast. But we're talking about like observing or detecting black holes, and with the one now very famous exception of the giant black hole at the center of a nearby galaxy, we've never actually imaged the event horizon of a black hole. This one with this massive effort using telescopes around the globe, the so-called Event Horizon Telescope. We have a very crude picture of the shadow of the actual black hole itself. Otherwise, every time we see them, and we've got excellent, strong data, observations that show that there's a black hole there, but it's all by seeing how fast stuff is swirling around it, or the energy coming from the stuff.
It's the effect of the black hole on its surroundings.
Right. Yeah. And so from that, we can say something about how massive it is.
Right. So for this particular black hole, for example, at 70 solar masses, 70 times the mass of our sun, this was determined by looking at. It's not alone, right? It's in a binary star system, so its companion star is whipping around the common center of mass of the system. And by figuring out how fast it's whipping around and what its orbital distance is, then you can calculate what the mass of this unseen partner is.
And this guy's in our galaxy here.
This guy's in our galaxy. It's kind of in between us and the center of the galaxy.
Are you gendering the black hole? Are you gendering the black hole?
I was. I'm trying to make guy not be a gendered word.
You can't do that.
I can't?
Late. It used to not be, and now it's
anyway. It's been regendered?
Yeah.
All right.
Well, this
also
object...
use guy. Okay. It's complicated.
This object is neither male or female or anything. It's just a black hole. And that's one of the cool things. It can't have a gender.
That's right.
It can only have mass,
charge,
spin, and charge.
Yeah. Right.
No gender. No gender. So anyway, this thing was about 70 solar masses, and it got a lot of press because most of this black holes that we find are stellar black holes. That is, they're black holes that formed when large stars die.
It's not that they're really awesome black holes.
No, they're not. They are awesome, but they tend to be smaller than the 70. They tend to be somewhere between 3 or 4 and 20-ish, 15 or 20 times the mass of the sun. And we kind of had thought that there's kind of a limit of about 25 solar masses or so to these things. And then, of course, there are the totally separate group of supermassive black holes.
Those
are millions or billions of times the mass of the sun formed in a different process. But that middle ground of black holes between about 25 and 1 million solar masses, we haven't seen much.
We talked about that a little bit.
We did talk about that a little bit in a recent episode. But this is a direct observation. I say direct observation, not an actual observation of the light from the black hole, because there is none, but an observation of a black hole pulling on a star that tells us that there's a 70 solar mass black hole. And it got a lot of press because it was impossible or it shouldn't be there. But in reality, this was another example of the press not doing a very good job of translating what the scientists had to say. In fact, it's not impossible at all. In fact, it's...
Because we saw it.
not only that, but we've seen other black holes in this size range. We've seen... In fact, that's what LIGO has been seeing over and over again. Remember, LIGO, the gravitational interferometer there that saw those gravitational waves that we've talked about on the podcast before. Mm-hmm. It's looking and finding these black hole mergers that are starting with 20, 30 solar mass black holes and ending up with 40, 50, 60, up to 80. I think the largest black hole seen so far ended up being 80 solar masses after the collision. So we've seen these black holes created before, and we know a mechanism to make them. You can just collide smaller black holes together to make bigger black holes. Right. In addition, we also think we have other mechanisms for this as well. We think that some stars that are extremely large will not go supernova, that they will, when they die, they will burn through their stuff very, very quickly and end up collapsing before they can turn into a supernova. and that will take all of their material and make it into a black hole rather than just the core, and so that'll end up with a black hole that is on this order, 50, 40, 50, 60.
Or
yeah.
so.
Okay.
So the headlines really get. I mean, it's great that people get excited about things like black holes, but you gotta do it right. There's plenty of cool things about this discovery.
But you gotta
That's what we do.
But it's not like an impossible black hole. It's not,
Calm the fork down.
It's in fact.
Yes.
That's a crazy fork.
So
But that's what we're here to do.
that's what we're here to do.
Bring reality.
Bring the reality. So it's an awesome thing. It's a cool discovery because it is the first of this size black hole that we've discovered in our galaxy. All right, although LIGO detections of these things have been distant and from distant galaxies. So it's the closest example of this. The first one we found in a binary star system, so that's cool, and it'll allow us to study it with a lot of more precision and stuff than the other one. So it's cool, but it's not like some new thing that shouldn't exist and does.
Okay.
Kind of like, I don't know, insert meme here.
Didn't mean to bring everybody down.
No, it's good. It's good. We've some reality.
Yeah.
Some black hole reality.
You didn't want to say anything about the shape of the universe?
No.
But speaking of black holes, or
our
galaxy.
I just love how that's just thrown out there. Did you want to say anything about the shape of the universe? No.
No.
On the next episode of Walk About the
episode,
Galaxy,
maybe.
we'll talk a little bit about some new shape of the universe news.
But there was a new finding, a new observation of the supernova
Oh yes,
1987A,
that's the other thing I wanted to talk about.
Which is not a black hole.
So that is an awesome thing, right? Supernova. So SN 1987A is what again?
It's in the Magellanic Cloud, actually, isn't it?
Yeah, it's not in our galaxy.
Yeah.
It's in
It's
in one of our
satellite
galaxies, right? The Large Magellanic Cloud, which is visible to the naked eye if you live in the southern hemisphere.
Right.
I've never seen it.
It's a dwarf galaxy. So dwarf meaning it doesn't have the hundreds of billions of stars like our galaxy, but it has hundreds of millions maybe of stars. But it kind of orbits very slowly our Milky Way, and
probably had some interactions with.
It's definitely it's a weirdly shaped galaxy. Cool. So it's because it's been warped. It's been all tidally warped by the gravitational influence from our galaxy. But
anyway,
it's the unruly mob lingering outside the well-ordered stadium.
That's right.
But
like
Supernova 1987A is a super famous one,
right?
Because it's one that we observed in 1987, and it was like one of the first ones that we were able to sort of observe.
Well, we had seen the star before it had blown up,
and then we saw it. We saw the whole collapse afterwards, and we've been able to observe it since then, and all that stuff. And it's been really well studied.
Really well studied, and very exciting for all of us because no supernova had gone off in our galaxy in the age of telescopes, since the 1600s. We were waiting for a supernova to go off so we could sit there and watch it. It hasn't happened, and it didn't in our galaxy, but
close enough.
Magellanic Cloud is so close that we got a really great view of it.
Yeah.
It's I was in grad school when that happened.
Oh yeah,
actually, and it's that's right.
You might be old.
I'm older than you. But
not as old as the star that made Supernova 1987A.
Damning by faint praise. And the predictions of how frequently a supernova should be popping off in the galaxy was that we were way overdue. Like it should be sort of every several decades or something like that, and it had been hundreds of years or something like that.
Mm-hmm.
Yeah. And this was one that's like, here's a star, we can like go look in the calendar, like, oh, that was star 397265, just blew up. Right. So we actually knew what that star was, where every other time we'd seen a supernova, it's just like in some distant galaxy, all of a sudden you see a star there that we don't know what it was, blew up.
Right.
But one of the big questions in the 30 years since this happened is, where is the star that should be still there at the center?
I was very young in grad school, by the way.
That's true. You were.
I was like a baby Yoda.
So when
he's 50.
So when a massive star goes supernova, there generally is something, well, not generally, essentially always something left behind.
Like a neutron star.
Like either a neutron star or a black hole. In this case, we predicted it should be a neutron star based on the size of the star that exploded. But
nobody's been able to see it.
Right, we haven't seen it. So what happened now?
So there were some predictions that probably the reason we couldn't see it was just that there was so much gas and dust that were still in that region that we couldn't see it. I think some people hypothesized that maybe there was enough stuff that it did eventually turn into a black hole. But other observations seem to think that there was something there, but it was hiding. And so the telescope we've talked a lot about recently, the ALMA telescope.
Cool telescope. Where is that?
It's in Atacama, so the high desert of Chile.
High desert of Chile. That's like the driest desert in the world, isn't it?
Yeah.
Something like that?
I think
probably,
it's
because it's so
Antarctica.
high.
Yeah.
Antarctica dry valleys are real dry
Yes.
too.
Right.
Yeah.
But that makes it very good for viewing in infrared, because infrared light gets absorbed by water.
Sub-millimeter IR sort of wavelengths is for ALMA.
Yeah.
And so they think they saw some very bright dust. Yay! But it's that bright because it's being sort of heated and illuminated by the neutron star.
Right.
Right. Very hot.
Very, very hot.
Dust.
I love some hot dust. Love me some hot dust.
So the neutron star is hot, just leftover heat, right, from the explosion of this. From what? Because this is the ember of that star.
Right. This is the leftover core
used to be the
from
core.
that star. Right?
So the surface of the sun is like about 6,000 Kelvin, which is our funny physics temperature scale, which means about 6,000 degrees C. But the core of the sun is like 10. What's the core of the sun? It's like 10 million Kelvin.
10 million Kelvin, right?
Right. So the cores of stars are crazy hot. So once the star stops being a star, you still got this like hot ember left over. So we're seeing dust heated up by that hot neutron star ember.
Yeah.
Cool.
Yeah, it's pretty cool. I mean, we have lots of awesome images of this sort of system in lots of different wavelengths because people have been studying it for so long, and now they have this with ALMA, and they think they found the neutron star. So it's pretty cool.
Yeah, neutron stars, I mean, the reason why this is one of the reasons it's so challenging, like you said, is kind of hidden by all this other stuff, but also neutron stars are darn hard to see. Unless, because they're typical neutron star is 10 or 20 kilometers in diameter. Seeing something that tiny, I mean, even if that thing is very, very hot, which it is, like 1 million Kelvin or something, but even if it's hot, the surface area is tiny, so it's just not giving off that many photons. So it's going to be very, very dim. We get lucky, of course, and see neutron stars often because neutron stars
they're magnetized.
Produce. Yeah, they have very powerful magnetic fields and spin, which produces these beams of radiation that and if you're in the path of those beams of radiation, we see them as pulsars. And then they're really easy to see because but if the geometry isn't right and those beams aren't pointed at you ever, then seeing a neutron star is very, very challenging, especially if it's not even in our galaxy.
Right. So following on what he said, every pulsar is a neutron star.
Right.
But for pulsar for us is like an observational term.
Right. So yeah, every pulsar is a neutron star, but not every neutron star appears to us as a pulsar.
Ooh, what a fun diagram!
It'll appear to somebody
those are those.
I was going to say it sounded like the lyrics for a song you could write. They're sort of like one of those. They might be giant songs. Every pulsar is a neutron star. I'm not the person to write
Don't worry, we're not going to start a band. Don't worry.
We have so many good band names though that we've come up with.
We have good band names, but no musical talent whatsoever.
Hey, watch yourself.
Or sorry, I'll speak only for myself.
Yes, you can speak for me as well on that front.
Okay. I have musical talent.
Okay, I believe that.
Yeah,
I used to.
Yeah.
Well, we have to answer the trivia.
Oh, damn it!
I was hoping to try to close the show.
I was hoping to dodge that trivia question,
but you can't do that because then the listeners would not know what the answer to the trivia was. So I won't read the whole quote again, but remember the question is who proposed the first reasonably correct solution to Olber's paradox? That reasonably correct solution being that the universe is really big, and that some stars are so far away that their light has not had time to reach us yet.
Whatever the answer is,
crazy.
I'm going to write my next paper in the style of that writing.
Yes, the writing was very nice.
Oh,
so
yes.
who wrote that? Was it A, Ernst Mach, B, Michael Faraday, C, Christian Huygens, D, Henrietta Swan Leavitt, or E, Edgar Allan Poe?
I so much want it to be Edgar Allan Poe, but I think Jim wants me to want it to be Edgar Allan Poe, and wants me to
the mind game.
There's so much psychology.
Guess that, and then but he also knows that that's what he would want me to want him to want, so that he actually thinks that I wouldn't do that one.
Right.
And he's right, I won't.
Okay, so what are you going to guess?
I'm just going to go Christian Huygens for
Cassini reasons.
But I thought he was earlier than 1848.
I thought so too.
So I'm not going to do Christian Huygens.
I'm
going to go Poe.
Oh, look at that!
Whoa!
I'm going to go woman power. Henrietta Swan Leavitt. I don't think that's the
fantastic. Josh, you got it today. It is, in fact, Edgar Allan Poe. You were saved by your last-minute recognition that Huygens was earlier.
Yes.
He was late
18th
1600s.
century or 17th century.
Yeah, he was very early. Henrietta Swan Leavitt was a bit later.
Oh, was she?
She was the late 1800s, early 1900s.
Okay.
And Michael Faraday is the right time period.
Oh.
What's up with Edgar Allan Poe?
But Edgar Allan Poe,
the Olbers
this
paradox.
is the weird thing. This is a weird bit of cosmological trivia that he was not a physicist, a cosmologist, an astronomer of any kind, but
That's awesome.
he was intelligent and well educated, and he kind of figured out what the solution was.
That's cool.
That's cool.
Yeah. While it may have felt like the time for the light from the most distant stars to arrive at your light-starved pupils, it was just another episode of Walkabout the Galaxy. If you liked this episode of Walkabout the Galaxy, write us a review and submit it as a book to the Kindle store. If you didn't, give it another listen. We think it will grow on you. Be sure to like us on Facebook to get all our updates and check out our website at walkaboutthegalaxy.com. Remember to check out the Are We There Yet podcast, hosted by Brendan Byrne, for all the latest space news on space exploration, featuring your astral quirks on an Ask the Expert section. Subscribe to our YouTube channel, Walkabout the Galaxy, where you can see our meaningless hand gestures. Catch up on old episodes wherever you get your podcasts, thanks to our listeners in Massachusetts and around the world. Follow us on Twitter
at @walk_the_galaxy.
And ask us questions anywhere using hashtag #WalkaboutTheGalaxy. Our theme music was composed by Richard Drusik. Our production assistant and video guru is Diego Rodriguez. I'm Josh Caldwell.
I'm Maddie Dove.
I'm Jim Cooney.
We're the Astro Quirks, signing off until the next episode of Walkabout the Galaxy.
Poe!